Do hyperparameters matter for causal discovery? And how to tune them for your double machine learning model?
Join us for 4 short conversations with leading causal AI researchers on hyperparameter tuning, causal representation learning, and causal effects of publishing your preprints on paper acceptance. This is Causal Bandits Extra at CLeaR 2024. Let's go!
Hello everyone, I am Damian Machlanski from University of Essex. And I'm happy to present you our recent work on robustness of algorithms for causal structure learning to hyperparameter choice.
Oh my God. What is your work about?
I'll start with the motivation of the paper. So it's fairly simple actually. We go from the place that we recognize that hyperparameters in supervised machine learning are very important. Essentially, many methods are very sensitive to the choice of hyperparameters. Another point is that at the moment, causal structure learning, so recovery of causal graphs from observational data, don't really work that well at the moment, especially not in applications like with real data sets. Because those methods rely on machine learning so much, I was wondering if those struggles in application can be due to hyperparameter choice.
Yes.
And also, something very important to note is that structure learning is unsupervised in nature. We don't have any information about causal graphs beforehand. We just have the data set and that's it, right? So we first explore very simple graphical example. We have 2 variables, x and y, so very simple bivariate case. And the idea is that because we have only 2 variables, what we can do as a very simple solution is to fit 2 regression functions. One is x on y and y on x, right? So we have 2 separate estimators. And then we can measure prediction error of the 2. And then how this very simple causal algorithm works is whichever regression line has lower prediction error, we conclude that, oh, this must be the correct causal direction. Whereas if the other has lower error, then conclusion is otherwise. Right? Now what we have on the x-axis is number of regression parameters. In the example, the general idea essentially is that as we change the number of regression parameters, so the coefficients in the regression, the answer of the causal direction will change, right? So for certain values, we will conclude that the causal direction is the right one, and for other number of coefficients, the answer will be the opposite, which is incorrect, right? And that number of coefficients, because we can control this as analysts, it's a hyperparameter, right? Like one hyperparameter. So that's the main message. As we change that hyperparameter, the answer differs, and mistakes are possible because of that, right? So that motivated our full study that we conducted. Many different simulated settings, but also one real data set, Schacht, and also fairly popular data generator syndrome. We measure 3 main metrics, structural Hamming distance, but also false positives and false negatives of the edges, right? But essentially for all of them, lower is better. In terms of hyperparameter selection, we cannot really do hyperparameter tuning because those methods at the moment don't really exist, or if they are very experimental. So we are just, in a way, we are in an abstract world, and we're assuming that we can perform some selection decisions, but we just kind of abuse the fact that they are simulated settings, right? We have 4 choices. One is the best hyperparameter values, which we can just call like Oracle. Like we assume that we have access to Oracle hyperparameter tuning. On the other end of spectrum, we have the worst possible hyperparameter values. And then something in between, we have either default values proposed by authors of algorithms or within packages. And we also have default values that we derive across all simulations, right? And now the main message, well, actually there are a few very important messages. The first one, which is very surprising, especially when we compare this to standard machine learning, is that default values perform actually surprisingly very close to Oracle cases. And that's surprising because in standard machine learning, usually default values perform very poorly. That was a very surprising finding here. Another one with respect to the Oracle cases is that, first of all, even when all algorithms have access to this Oracle, they still differ in performance. So that means that model select or algorithm selection is actually very important, regardless of hyperparameters. And another important point is that even with this oracle, there is still room for improvement for all the algorithms. Like we still see that there is still more work needed, even if we have near optimal hyperparameters. Another point with respect to the worst possible hyperparameter values is that we can see that, again, the extent to which the methods can perform badly also varies, which means essentially that I'd like, for example, to interpret this worst case scenario as safety of use of the methods, right? So essentially, if certain methods lower values in the worst cases, they are essentially safer to use than the other ones. Like, for example, neural network-based methods appear to be fairly risky to use in those cases, which is kind of expected because neural networks are known to be fairly volatile and sensitive to hyperparameters. And lastly, in this particular place we are, very important message is that even though we still have mistakes, even with the oracle cases, the number of false positives reduces pretty much to zero. So the only remaining mistakes we have are due to false negatives, which means, in practical terms, that in those fairly well-specified hyperparameter cases, whatever answers we have from the algorithms, the graphs and the edges, even though some of the edges can be missing, but the ones we have can be trusted as like this is true. Right? I think this is very useful. Can be useful in many cases, right? It's not totally false what we get. What I also like, one of the messages I like to pass along here is that when we compile a list or a table of the best algorithmic choices across different settings, and we can see that the best choice will vary not only across dataset settings, right? So like size of the graphs and edge density, but also the choices will vary when we consider different hyperparameters or different quality of hyperparameters, right? So for example, certain methods will be preferential if we consider that we can perform tuning somehow, whereas other methods will be safer to use if we consider the worst possible cases in terms of hyperparameter misspecification, right? So I think that's something worth keeping in mind in terms of choices.
What impact of this work would you like to see in the real world?
I think that the singular thing that I would like to, the message I would like to send is that to practitioners perhaps to, as I said just a few seconds before, whenever people try to select the best algorithms for their case, they should consider not only the data set that they have at hand, but also how hyperparameter tuning can impact that optimal choice, right? So, for example, are you confident that the values that you're setting hyperparameters are actually like optimal, or maybe like if your risk is your case is risk sensitive, then maybe it's better to focus on safer methods. That's my main message.
What should people type in Google in order to find your work?
You can find me on Google Scholar, Damian Machlanski. You can also find me on X, on LinkedIn. Usually it's at the Machlanski. That's my usual handle.
What's the best Causal paper you read last quarter?
I don't fully remember the title, but it's about hyperparameters and performance on the bounds, on decision bounds between hyperparameters. Like it just matters. Perfect visualizations.
Thank you, Dana.
Thank you.
My name is Oliver Schacht, and I'm a PhD student at Martin Spindler's lab at the University of Hamburg.
What is your work about, the one you're presenting?
So my work is about hyperparameter tuning for causal machine learning. We are working with the double machine learning framework, and our basic idea was that often the story is told how predictive machine learning is failing at causal inference tasks, but could it also be that causal inference is failing at the predictive machine learning? Because in theory, when you run double machine learning, you should get good results as long as you use good estimators, sample splitting, and also a Niemann orthogonal scoring function. But what we find out is that it's also up to many tuning choices, such as the hyperparameters for the nuisance estimation, so for the estimation of the influence functions, and also the choice of the causal model, and of course the choice of the learner, so lasso, random forest, plays a very important role.
What are key results from this paper?
Our key results are that actually tuning your machine learning methods for the nuisance estimation on the full data or on the faults of the double machine learning algorithm are the preferred options in small sample sizes over doing a train test split. Another key finding is that if you wonder which causal model and the incorporated structural assumptions are the right ones for your particular data, then you might want to track some sort of predictive loss on your outcome Y and compare it between different causal models. And the direction of advantage in this metrics points in many of our tried DGPs. So we tried 16 different DGPs, and in many of them it points in the same direction as the loss on the causal parameter, which is a good result because you don't need an Oracle estimate to compute this metric. And the final finding we had is that you can combine calculate some sort of combined loss between both of your nuisance estimates. So in this case, you have one estimate, which is a propensity score of treatment assignment on D, and one is an outcome model on Y. And if you combine the loss on both of these models, then look at a small value for that. This might indicate the right parameter tuning to achieve also a small loss on your causal parameter of interest.
Regarding the particular algorithms like base learners, does this work leads to any conclusions that could be helpful for practitioners?
Of course, the choice of the right machine learning method heavily depends on the sort of the data generating process. This is really something we can see in our paper. We have the full results for all DGPs, and it's very different. Of course, in the linear settings, Lasso might perform very well, while in heavily nonlinear settings, boosting algorithm is preferable. Something which we found novel on this is that we used automated machine learning algorithm in terms of FLAML, the FLAML framework, and we found out that this is maybe something that fits well for all data generating processes. This might be also interesting for a practitioner to look at this framework for tuning.
What impact of this work would you like to see?
A small level, of course, I hope that people who apply the double machine learning framework, but also causal machine learning in general, let it be in business or in industry, have a better hint on how, or better guidance on how to tune their choices, such as causal models, hyperparameters, machine learning methods. But on a bigger scale, of course, I also hope that I can have an impact on that, causal machine learning is applied more in industry, because right now I think there are many question marks and maybe also skepticism. And when there's more work on the practical application, I hope that people will use it more.
What should people type in Google in order to find your work?
They should type in hyperparameter tuning for causal inference with double machine learning. But in more general, I also recommend looking at the website of our software package. So I'm part of the team that develops the DoubleML package. You can check our website, docs.doubleml.org, and you will find many exciting examples and also documentation for double machine learning and for this specific project.
What is the best causal paper you read last week?
So recently, a colleague of mine had did some work about how to implement deep learning into the double machine learning framework. The paper is called DoubleML Deep. You will find it on ArXiv by typing in that. And I think it's very exciting because they can now also use as the nuisance not only tabular data, but also images and texts. And of course, when you have, for example, price elasticity estimation using images of products or product descriptions are very exciting. So I'm not involved in that, but I read their paper recently for the first time, and I think it's totally an exciting project, and I hope I will learn more about it soon.
Great. Thank you so much, Alex.
Thank you, Alex.
My name is Yanai Elazar. I'm a postdoc at the Allen Institute for AI and the University of Washington.
The work you presented here, what is it about?
Estimating the causal effect of early archiving on acceptance And the idea is to, we have papers and we put them often on ArXiv. That's the main way of putting a work out there besides the actual conference. I'm coming from the NLP community, and until very recently we had this anonymity period. And the assumption of the main reason for having the anonymity period, at least at the time of starting that, was to not have some certain people with certain affiliation on, more famous people have an advantage over other kinds of groups when they put the paper on ArXiv, so they won't get any other treatment when making decision on paper acceptance. And we had this policy from about 2017 until very recently. And we actually wanted to check whether this assumption holds in practice. Basically what we did is we took papers, so observational data, where we had data about the acceptance, the authors, and different other kinds of variables, and we tried to answer the question whether different groups have different acceptance rates based on those different variables. The difficulty was that in practice there's hidden confounders like paper quality, right? So you could assume that people that really believe in the paper, believe they did high quality work, would like to put a paper on ArXiv because they believe it's ready and high quality and want other people to read it. On the other hand, maybe people that less quality paper, they may perhaps mainly submit to the conference in order to get feedback and to improve that. So this is a very strong confounder, but it's also hidden. And besides the fact that it's hard to quantify it or to define it, it's also hard to quantify it in practice. So what we did is use a framework called the negative control outcome, which basically means that you need to come up with another variable that has the same confounders, like quality, and we can use that in order to deconfound its effect. So in practice, what we used is the variable of the number of citations of the paper after n years. This variable with difference framework, we were able to deconfound the variable and get some estimation about the exact effect that we're interested in. For the results, there are different setups and different assumptions that we had to make, but the first one was that without taking that quality confounding factor into account, we saw that there are benefits of putting your paper on ArXiv early. On the other hand, when we did use a negative control outcome and the difference in difference framework, we were able to show that there's actually not much of an effect. And even when in the cases where there was an effect, the effect was not statistically different between different groups. And those groups were number of citation and institution ranking, which were the main reason for having the anonymity period for the first place. A funny bit was that the day that we got the results of acceptance to CLeaR was the same day that the anonymity period was removed from the ACL community.
What impact of your work would you like to see in the real world?
Well, things like removing the anonymity period. No, but more seriously, I think it's an important problem and something that's important to continue monitoring. And there could be potential good reason of having that. I think that it's important to monitor and check if those things happen in practice. More generally, I think this was like more of a side project. In general, I'm interested in the connection between data and model behavior and about the interpretability of models through the data. And we would like to see more work on that. Will allow us to better understand models and understand the mechanism.
What should people type in Google in order to find your work?
My name, probably can find out my website, and all of my work would be there.
What's the best causal paper you read last quarter?
Probably one of Atticus Geiger. He presented here one of his work about causal abstractions.
Thank you.
Thank you.
Hi, I'm Simon Bing. My affiliation is TU Berlin in Germany.
What is the work you're presenting here about?
So the work here is about an identifiability result for causal representation learning, where the main contribution is that we can soften a very ubiquitous assumption that previous works make, where we consider multiple environments for causal representation learning, and usually these environments are characterized by different interventions on the latent variables. And previous works, a wide range of them, assume that in each environment we can only intervene on a single variable, so we have these atomic or single-node interventions. And we present one of the first results where for unknown intervention targets, we can allow for multi-node interventions. So that means in one environment, we can intervene on many nodes at the same time and still achieve identifiability. Yeah.
What are the main results from this paper?
The main results are that we can characterize a specific notion of sparsity and kind of operationalize this notion of the sparse mechanism shift hypothesis, that if we go from one environment to the next and we posit some kind of underlying structural causal model, that the change in terms of the mechanisms that are affected by interventions from one environment to the next is sparse. And by kind of using this basic principle in our setting, where the key assumptions that we make are we have a linear mixing function from the latent variables to the observed variables, and the kind of coverage of the interventions across the environments is sufficiently diverse and sparse in the sense that I outlined before, that then by regularizing precisely for this notion of sparsity, we can recover the underlying causal variables up to the indeterminacy of a permutation and element-wise rescaling.
What impact of this work would you like to see in the real world?
In the real world, ideally, hopefully in the long term, my group, we are thinking about how to apply causal inference and also causal representation learning to large-scale climate data. So we have very high-dimensional measurements, and how we can extract some causal information or formulate causal models about macro climate phenomena. And ideally, I would like to see this being one of the bases for which we can build some work that can then be applied in the real world, especially because we have heterogeneous data, but we collect it from different environments, and we can't actively perform interventions on the climate, as you might imagine. And so I think this moving away from the single node to the multi-node interventional environment setting could be an important first step.
What should people type in Google in order to find this work?
Multi-node interventional causal representation learning. Yeah.
What's the best causal paper you read last quarter?
So last quarter, one of my favorite causal papers that I read was unsurprisingly about representation learning, and it's called Identifying Representations for Intervention Extrapolation by Sorowit Sengkyongyam from ETH Zurich, where they have a real use case for causal representation learning, which I think could still, or was still missing before this.
Thank you so much.
Thanks a lot.